Fish started. So we'll start with your question and I'll double back to Devin's again just to make sure everybody's aware of it. So when we talk about solvents, almost exclusively you'll hear reference to polar and non-polar, right? And those are horrible definitions or horrible things because when you ask someone to define polar, they can't. They go, oh, well, it has a dipole. Well, that's not necessarily true of all polar solvents. So the best classification that I think works most broadly is going back to intermolecular forces. So if we're looking at a polar solvent, it is one that has bonds that are polar covalent. Those bonds generate forces that would be dipole-dipole or hydrogen bonding. A nonpolar solvent has bonds that are nonpolar covalent. Whoops. Nonpolar covalent and forces that are London dispersion forces. And this is the best kind of system to it because if we think through what the point is of a solvent, it's to dissolve things. Well, things dissolve based off of similar forces. So if I rank or create a naming system for my solvents that applies to intermolecular forces, that works. Right? So my nonpolar solvents have London dispersion forces. My polar solvents have dipole-dipole or hydrogen bonding. And this is why we actually have to create a new definition, because our polar has two possible force systems in it, and those have very different strengths of interaction, which is why what we end up doing is subdividing the polar category according to those two forces. And we get protic versus aprotic. Officially, the nonpolar can be called aprotic. They cannot be called protic, because protic means we have hydrogen bonding, and if we have hydrogen bonding, you don't have nonpolar covalent bonds. Does that make sense? Okay. So it's our polar category that breaks down into protic and aprotic, and all those are referencing is that a protic one involves forces that are hydrogen bonding. And the aprotic is one that does not. No hydrogen bonding. This is going to be dipole-dipole. So all we're trying to do is come up with ways that we can classify that solvent without having to label all the forces. Why don't we just label the forces? That's a good question. I don't have an answer. We stick with calling them based off of these kind of crude categories. Because protic is by definition polar, I drop the polar term from protic polar. Aprotic could hit a gray area. So typically I would go through and write aprotic polar. The nonpolar, by definition, is going to be aprotic, which is why I dropped the aprotic on that part. Like, it can't be protic. So that really sets up three categories. You get your nonpolar, you get your protic, and then you'd get this aprotic polar, or polar aprotic, I think that's typically how people phrase it. And that's all those different categories are. They're ultimately based off of the strongest force that that molecule could exert.
That helps a lot.
Yeah? Okay, I just want to make sure. Because it looks like maybe you got another question in there.
Not now.
No? Okay. Okay, just checking. And then before everybody came in, we can actually go ahead and just pull up that worksheet, not that button. What button am I doing? Oh, it's the button on the computer. Course modules, that was week 7, right?
Yeah.
Devin? In the week 7 assignment, there's this question.
Number 4.
Provide a brief definition for each reactivity class and provide a simple structure that clearly exemplifies that class or that definition. I don't have a good way of asking this question This is one of those things of, this is an important concept I want people to know, but I want you thinking and trying to figure out what those things are that move to it. So when we're talking about our reactivity classes, we're saying not the definition of reactions, because that's how do I get from AB to CD. I don't care about that. What I care about is the reactant. What did A act like when it reacted with B? What did it do? That's the reactivity class that we're trying to reference. So if we were looking at a diagram, we could say A plus B went to C plus D. Naming the reaction is effectively referencing that reaction arrow. What I'm asking is that if this somehow does something to that action is what I'm calling a reactivity class. Right? And there's 4 classes for it. It's what are those things acting as? Right? And we did talk through those, but the phrasing is so weird that that's hard for anybody to actually acknowledge. Right? And if we go through with our simple reactions, the easiest reaction is an acid-base reaction. So if this was an acid-base reaction, what do you think A acted as? Acid. Why do you think that? It begins with A. That's perfectly acceptable. That's fine, okay? Because we haven't provided any other classification behind it. Okay? What would we need to see if we think A was an acid? What genuine characteristic should we find in that molecule? It needs to be an H plus donor. Okay? So A here, you're saying, well, I think Mike is calling that an acid, and the B is probably a base because they both begin with those letters. Okay? But you're really just guessing at this system. If we were to look at actual structure, what should that structure A have? That structure A should have some form of positive hydrogen within it. Okay? There's a slight problem with that, and that problem is that if you have a positive hydrogen, it's not bonded to anything else. Okay? So if we're looking at an acid within a reaction, the hydrogen's always going to be bonded to something else. But that something else needs to be willing to take the electrons away from the hydrogen, so I have a strong partial positive hydrogen. That would be a good example for protic solvents, because they're giving up protons, or hydrogen ions. Okay? What do acids react with? Bases. What's the definition of a base? It's our hydrogen ion acceptor. Okay? And what we'll encounter is that base definition is tricky, because if I just draw a structure, how do I know it is accepting hydrogens? Said another way, if I draw OH minus, okay, and I do a chemical reaction with OH minus, is that a base?
Yes.
Yeah?
Well, no, it's an acid. Sorry.
What happened in the course of this reaction? What did that OH do
Bonded to that carbon.
to that carbon? How did it make that bond?
By donating electrons.
It donated electrons to that positive charge. Is that positive atom a hydrogen? No. So did we change the location of a hydrogen atom? No. Which means did we run an acid-base reaction? No. Is it acting as a base? No. Because the base needs to accept a hydrogen. It didn't do that. Okay? So of course I was rude because I made Devin wrong. But could Devin have just as easily been correct? What if I said the product was H2O? What did the OH minus react with? It reacted with a positive hydrogen. Now Devin's correct. So the only time we really know whether a base is something that acted as a base is when we look at the full reaction. We have to see what it is reacting with. The acid is donating protons. The proton's there, and we'd be like, that's a positive proton. I can see that reacting. We could predict acid characteristics. predicting whether something was acting as a base or not becomes a little bit more questionable because we actually have to look at the reaction to see what it's doing. We have to see that action. Okay? And in this case, it is accepting that proton. If we flipped it back to the one that I had, this scenario, is it accepting a proton?
No.
So a proton is H plus. Did H plus react at all in this chemical equation? Oh, I see an H here. There was also an H here. Did that H do anything? No. So did it transfer hydrogens? No, which means how do I classify that reactivity? I can't classify it as an acid or a base because it didn't match those definitions. That's why we have two new definitions. Okay? And we could expand and call it the Lewis acid-base definition, but the Lewis acid-base definition applies to everything, so it doesn't allow me to nuance, oh, that's a transfer of a hydrogen versus that's a transfer of something else. This is why I tend to ignore the Lewis acid-base definition, and we add in a new one that we call, and I'll try and align them appropriately, electrophile and nucleophile. I spelled electrophile a little weird. Okay. What is the definition of either one of those? Pick one. And this becomes the challenge. Okay, file. Have you ever heard the word file before?
Not in a good context.
Not in a good context, and unfortunately that's the only one that I remember too. We won't record it, but think in that bad context, what is that referencing? What does the file mean?
Unwanted content.
It doesn't mean unwanted contact. I got a good one. Bibliophile.
Liking something.
File just means like. That's it. Okay? So if we're looking at this, this means like. Right? Like in that loving context, not like as in similar. Okay? What is electro? Well, that's electrons. So an electrophile is electron loving. If it is electron loving, what must it look like?
Something that wants electrons.
What would be something that wants electrons?
Something that's positive.
It has to have positive. It can't be negative, because if it was negative and wanted electrons, it's getting more and more charged. Okay? We try to push to that neutrality. So this becomes an electron acceptor, and these are typically positively charged. What did your acid do? It donated H+. Donated H+ by doing what? Accepting electrons. Okay? So the acid and the electrophile definitions really float in similar areas. Okay? The electrons are ultimately doing identical things. It's just what they're acting on. Acids and bases, our electrons are acting on hydrogens, and so we decide to use the hydrogen as the definition. Our electrophiles, nucleophiles are acting on things that are not hydrogen, and therefore we reference them based off of the electrons. So if an electrophile is electron acceptor, what is the nucleophile? An electron donor. Does the name give us that too? Well, it says phile, meaning loving, and it says nucleo. What is nucleo? Nucleus. And what's in the nucleus? Protons. What charge are protons? Positive. So if we're finding something that is positive loving, what must it have a lot of? Electrons to donate, because it's trying to interact with that positive to cancel that charge. Kind of, sort of? So when I'm asking for reactant classes, that's what I want you to pull at. Those four definitions are critical, so that when you look at a reaction and you look at a reactant, you can be like, I think that's going to act as a nucleophile. As soon as you've identified that it acts as a nucleophile, guess what the other thing must act as? An electrophile. You now have a possible prediction of what the product is, just based off of following the rules of those definitions. That's why it's super important to have those nailed down. And I guarantee you, I will ask you explicitly for one or all of those definitions. Okay? Kind of, sort of?
Then, wait, on the question number 6, I feel like it asks pretty much the same thing as number 4.
Potentially.
6.
Reactivity, as in it's the species that's doing the action. Okay, that was the A or the B in the course of the reaction. What's question 6 asking? Reaction. I don't care about the reactivity. I care now what's the overall picture of what's happening.
Okay.
That's now each of your reactions. That's acid-base. That's substitution. That's elimination. That's addition. That's radical. Okay? Why do you need to know those? Because if you know those, you can start to classify the chemicals that are necessary to allow each of those things to occur. Right? It helps categorize the reagents that ultimately show up in the next system or the next rest of the semester. Okay? So what I'm asking for here, and unfortunately a very tiny space, like I thought through it, I was like, should I provide a really big space? Because this is a really big question, or just let people figure it out? And I decided to just let people figure it out. Okay? So the spacing within these things is not well thought out at all. It's pretty much just, I just want to get the questions in as short a space as possible. So some of them may take a lot of volume, some of them may not. So don't assume that's a short answer because it's a small space. Okay? Exam is entirely different because you're supposed to write it all on the exam. So if you see a large space on the exam, it's probably because I'm expecting a large answer. Okay? Make sense? Hi. Should we take a look at some of these? Okay, cool. Okay, it says which of the following is an acid-base mechanistic step. Okay, well, acid-base is the straightforward one. If it's an acid-base step, what do you expect to find in it? Transfer of a hydrogen. Okay, so an acid-base reaction is just the transfer of H+. Okay, so what we could go through and do is look at each of these reactions and say, okay, which of these caused a hydrogen to transfer places? One of the things that is immediately more challenging with this, if we're talking about a transfer, we're saying it goes from one place to another place. That's kind of like looking at beginning to end for a reaction, the reactant and the product. Have we shown the products?
No.
What is a good first step to attempting this question? Draw the products. So do it. Okay? You got 4 things listed out here. Again, I know the spacing is a little bit cramped there. Okay? But draw 4 products. And if you got questions on what to do, you can. So I don't know if you guys heard me. I was talking in the back. A is by far the hardest one on this. B, C, and D are a little bit more reasonable, but even then, there are some challenges behind these. And a lot of this is new. You're moving electrons in ways that you haven't done before. Okay, so if we take a look at A, what is happening?
Pi bond's being broken.
A pi bond is being broken. We're showing the electrons in the pi bond moving and being shared with the hydrogen, which means at a minimum, when we draw the product, that pi bond had better not be there. Okay, because that's what that arrow means. We had our arrow start in the pi bond and we moved 2 electrons. How do we know we moved 2 electrons and not 4? Or 1 or 3? Say it again? True.
An arrow only indicates moving 2 electrons.
Not all arrows indicate the movement of 2 electrons. Said another way, This arrow in purple indicates the movement of one electron. Why is my purple arrow different from all the other arrows?
It has one little thing.
If you look at the arrow head, most of the arrows we work with have two heads. Each of those heads happens to represent a single electron. And if you want to move one electron, you use a single-headed arrow. We don't have an ability to move more than two electrons. It's either one or two, and that's it. So when we're looking at that first arrow, this is insanely small on my screen, which means it's really small on yours too. That first arrow has two heads, and what we're doing is saying we're taking the electrons in that bond and moving them. Devin said the pi bond. It's a double bond, so there's two bonds there. What are the two bonds that are present in that space? Sigma and pi.
Oh, sigma and pi. Sorry.
Why'd you move the pi and not the sigma?
Because the pi builds on the sigma.
It's a good way to phrase it. The pi builds on the sigma. The pi is a higher energy bond. That's going to be the first one to react. Fantastic. Okay, so you're taking those two electrons, and what are you doing with them?
Moving them to the hydrogen.
Moving them to the hydrogen. Does that mean I should be saying like that?
Another arrow.
Okay, there's another arrow. So you're saying maybe I should address that other arrow first? We can do that. What does that other arrow mean?
You're breaking the sigma bond.
I'm breaking the sigma bond. Where am I taking those sigma electrons?
Bromine.
I'm putting them on the bromine. So my bromine still has the three lone pairs that we drew in, and now it has that extra pair of electrons from that sigma bond to the hydrogen. So what's left with our hydrogen? Where is it? Where is it? Right? Is that a proper sentence?
Yeah.
Where is it? Yeah. Okay, sorry, it sounded really weird. Where should I draw that hydrogen in my product? On the paper. Yeah. It's a good start.
If there's two arrows giving and taking electrons from one thing, doesn't that just kind of cancel each other out in the bond space?
What it cancels out, so there's two arrows, you're right. That blue arrow showing hydrogen losing electrons, the red arrow showing hydrogen gaining electrons, which means the net result is the charge on hydrogen must stay the same. The bonds are still moving, but the balance of electrons on that atom has to stay the same. Right? So the first thing we do, maybe the hydrogen's here. What happened to the bond to its right with the bromine? That's gone, so I shouldn't show a line there anymore. Okay, so that has to disappear. Well, what did the line on the left mean? Or not the line, the arrow on the left mean? Okay, how do I do that? Nate, you said no. Why not?
Isn't it already implied that it has electrons, so adding to wouldn't that make
No, and hydrogen doesn't have any extra electrons. It only comes in with one. One was in that bond, the blue bond. That electron went with the bromine. So after that blue arrow, that hydrogen has nothing. We then have this red arrow. Well, the red arrow shows the motion of two electrons. What we're trying to decide is, what does that arrow mean? Does that mean both of those electrons sit on the hydrogen? Say it again? It needs to be a bond. So what we're doing is moving those pi electrons from being in a pi bond to now saying, I want them in a sigma bond. And I want them in a sigma bond with the hydrogen. But a bond requires two atoms. Hydrogen's one of them. Where's the other one? Right? So a safe bet would be carbon, because it's an organic chemistry class, right? Okay, and the vast other atoms present are carbon, so it makes sense to put it as carbon, but now the question becomes which carbon? Would you call it this purple carbon here? That purple dot. Does that make sense? No, why not? The arrow isn't affecting that carbon, so that doesn't make sense. How about this one? No. This one? Could be. Okay, I accept that. This one? Could be. Okay. What we're now addressing is there's two places that hydrogen could be connected. It could either be connected at the purple or at the green. Okay? At this stage, do you know the chemistry? I know it's a dangerous question. I'm going to take silence to mean only one answer, and that one answer being, no, I don't know this chemistry, Mike. That was a stupid question. Don't ask me that. Okay? And it's fair to say you don't know. Okay, so you don't know. If you don't know, what should you do?
Try it anyways.
Flip and guess. Yeah, let's just attach it. Okay, we know it has to go to one of those two positions. We just don't know which one. Okay, so let's pick one. Let's say it goes to the purple. I know, that looks ugly. Oh, I don't like ugly bonds. Then make it look pretty. It doesn't need to look pretty. Okay? That's sort of mostly acceptable. Why is it also mostly unacceptable? What have we just drawn? Some carbon structures. Cool. So we're drawing Lewis structures. And what's the last step of drawing a Lewis structure? Assigning formal. Did you assign any formal charge? I know I didn't. Okay, so maybe we should assign formal charge. We go through and assign formal charge. What do we notice?
That the green guy. Wait, I'm lost.
Did you assign formal charge?
No.
No, okay, so assign formal charge. Where do you think you should assign formal charge? I would argue there's 4 places that you should be considering, and only 4 places. The 2 carbons, because they had a pi bond and now you removed that pi bond, so it makes sense to look at their formal charge. What else? The bromine and the hydrogen. Why? Those were the only atoms involved with the arrows. Yeah, it makes sense to look at formal charge for all of those. We technically already addressed the hydrogen. The blue arrow said hydrogen loses electrons. The red arrow says hydrogen gains electrons, which means the hydrogen neutral. I don't have to worry about it. We got 3 other atoms. Take your pick. Say it again? Purple one. How do you calculate formal charge?
Valence electrons.
Pause. How many valence electrons does carbon have? 4. Continue.
Minus lone pairs.
How many lone pairs does that purple one have?
None. Minus bonds.
How many bonds?
4.
Which means?
It's neutral.
0, which means I don't need to specify a charge on that carbon atom. Okay. Now what should we do?
Green.
Green one.
4.
4 minus?
0.
Minus?
2.
Why only 2?
Because you got rid of one of those pi bonds. Oh wait, there was an implied hydrogen on the next, so it's 3.
Remember how I said implied hydrogens could be problematic? If we go all the way back to that beginning, I think one person I saw actually draw in that there was an implied hydrogen there. It's important, okay? Which means when we get to that product, what happens? There's still that implied hydrogen there, which then means still 0 non-bonding pairs. But now how many bonds? It has 3 bonds, which means it is positively charged. That carbon is positively charged. This should scream at us that we've got a problem. Why should it scream at us?
Because there wasn't a charge to begin with.
When we run a chemical reaction, we cannot create or destroy matter. Electrons are part of matter, which means we've created charge. We've somehow lost an electron in the course of this reaction. Or that means we didn't finish calculating formal charge for all of our atoms. And sure enough, we didn't look at bromine. How do we calculate formal charge for bromine? 7 minus,
8 minus
which means a negative 1. Okay? What you have now done is predicted one possible outcome. What do you mean one possible outcome? I mean, this particular reaction, unfortunately, has another possible outcome. The bromine is going to be the same, but now that other possible outcome is going to be what? Where the hydrogen is connected to the other carbon. When we go through and calculate formal charge there, guess what? We're going to find the positive charge there. Okay? And you're right. Now we've got an interesting dilemma. How do we know which one was correct? I would argue you have the ability right now to determine which one is correct. That's challenging. We've not explicitly talked about this chemical reaction, and so you don't have the exact context behind it, but we've talked about how chemical reactions work and what they try to do. When a chemical reaction runs, what does it try to do?
Revert back after it's.
Why would it revert back? Why do reactions revert backwards?
Because it doesn't like the charge on the right.
Ah, okay, it doesn't like the charge. Charge is bad, it would revert backwards. But if we're saying the chemical reaction happens, which of these should it produce? If I now say it has to go forward, it doesn't have to go forward a lot, but it has to go forward, does it produce each of these to an equal amount? Why did it go backwards?
Because it doesn't like either.
Be more specific. It didn't like what?
The charge on
The charge, which means if I'm going to go through and progress to make either one of these products, which product is going to be the favored one? The one that is less charged. You're like, but they're both positively charged. You're right. Does that mean they are equally positively charged? No. Is there a difference about where that positive charge is located? Yes. What is that difference?
whether it's on this first or the second part.
Say it again.
One's further away from
No, the negative is sitting out here in the middle, so I'm going to say they're equidistant.
one has more electrons than
What do you mean?
like the one on the right, the positive charge has a lot more electrons around it, therefore it's able to kind of.
What do you mean? That's 2, 4, 6 electrons. 2, 4, 6 electrons. It has 6. 6 and 6. I don't understand.
The electron.
No, you're right. Keep digging.
Because the hydrogen is different. Yeah.
The hydrogen is different than what? Than carbon. How is hydrogen different than carbon?
Valence electrons.
The amount of electrons. Carbon has 4 valence electrons. Hydrogen has 1. This carbon has how many valence electrons? 4. 4. The hydrogen has 1. How many electrons are around that positive charge? We said 4, 4,
10.
and 1,
Oh, 9.
9. How many around this one? 4, 4, 4. This one has 12 electrons around it. This one has 9. Which one is going to be more stable? The one with more electrons around the positive charge. That's flippin' crazy. You can predict where the hydrogen goes because you look at the stability of the products. I don't know which one it is, so you draw them both. And then you look for the difference between those both to then decide which one was more or less stable. Can you do that? Yeah, that's why OChem is so cool. We're looking at layering how those things are reactive and how they aren't. This is why it's so important to know those definitions. Why is it important to be positive? What is a positive? It's missing electrons. How do I make it more stable? Give it more electrons. Well, that one has 12 electrons, that one has 9. 12 electrons is more stable. Really? Yes. That's cool. Okay? We went down a neat little rabbit hole there because that didn't have anything to do with answering the question that was asked. But that's a fun little rabbit hole. Is that something you will be responsible for? Yes, absolutely. Okay, so what does that mean? If we're going to predict the products, this is our better product system, so we can erase that first one we drew. Okay, so what happened in the course of this reaction? So now we'll erase all my colors out of that. We can try and clean that up, make it a little bit easier to see. What changed? The hydrogen went from the bromine structure to the carbon structure.
But
I like the, I'm going to say it. I like your butt, but not yet.
okay.
Okay, we transferred a hydrogen, right?
Yes.
So isn't that acid-base?
Not necessarily.
Not necessarily. Okay, so what's your butt?
A pi bond is broken.
The acid-base is only the transfer of a hydrogen. That's it. I also broke a pi bond.
Addition.
Okay? Because I also broke a pi bond, it's not acid-base, it's addition. So it's an addition reaction that involved an acid. And technically, if I were to label this, this is acting as a base. And what reaction do I get when I mix an acid with a base? Well, that's acid, except this is an addition. Damn it. Okay? Because I've lost that pi bond. So this is why it's really important to know those definitions and why you should be bringing in the but it doesn't fit this part of that definition. Great job.
I'm confused.
Okay.
Because in the definition it says breaking of a pi bond and formation of 2 sigma bonds, but we only formed 1 sigma bond.
Well, but officially this isn't an acid-base reaction.
Yeah.
So you're trying to, so you're looking at an addition reaction. This isn't an addition reaction, this would be an addition mechanistic step. The addition mechanistic step splits into 2 different types of mechanisms. Okay? And so that is at the tail end, getting way deep into the mechanistic labeling. So for a reaction, we could call this an addition. Is it an addition mechanism? Yes. Which addition mechanism is it? Okay. Well, when did the pi bond break? The pi bond broke when we added a positively charged species. Okay. So how many of you know all your mechanisms or have some passing familiarity with them? You may not. That's okay. I'm just asking. Okay. So this is where you should go back and you should review all those mechanistic steps. I can't double out to show the list. But when we look at addition, there's 2 types of addition. There's electrophile addition, and there's nucleophile addition. What charge are nucleophiles?
Negative.
Negative, per your notes that you just took 10 minutes ago. When the pi bond breaks, is it because it's reacting with a negative?
No.
No. So is this nucleophile addition?
No.
No. Okay. The other type of addition is electrophile addition. An electrophile is positively charged. When the pi bond breaks, what's it reacting with?
Hydrogen.
What charge is that hydrogen?
Positive.
Positively charged, which means this is an electrophile addition. Wow. This is why we really drill into each of those definitions to acknowledge what's happening at each of those stages. Kind of make sense? Okay. Can I erase A? You guys want to try and do B, C, D now on your own? B's also kind of a hard one. Man, which one's more straightforward? C and D are straightforward. Yes, I fully accept. I can vouch C and D are straightforward. B is a little challenging. I think it's easier than A, but it's still challenging. You guys want to try C or D? Okay. What are you guys going to try, C or D? C. Okay, everybody work on C. We'll go with 2 arrows again. We've got a red arrow. We'll call it a blue arrow. Which arrow do you want to look at first? Blue arrow, okay. What does that blue arrow mean?
Hydrogen's giving electrons to
I'm going to say it's not hydrogen giving the electrons.
the bond.
Much better. The bond between the hydrogen and oxygen is now fully moving to the oxygen, which means that oxygen has gained, whoops, I did an eraser, has now gained that pair of electrons, and our hydrogen is now floating off, not connected to it. Okay, I'm ignoring charge for the moment because I've only done half of the mechanism. The other half is dealing with the red half. Right? So are we okay with that? What happened on the red half? What does that red arrow show?
Oxygen sharing electrons with hydrogen.
That oxygen shares a lone pair of electrons with the hydrogen. If it shares electrons, what has it done?
Creating a sigma bond.
It's created a sigma bond. You're like, oh, it's an ugly bond. We don't care how it looks necessarily as long as it is technically correct. Does that make sense? Okay. What we've now done is the bond transferring. Okay, the making and breaking of bonds. Before we finalize and say we're done, can we now start to answer the question? We should do the last step of drawing our Lewis structure, which is formal charge. All the atoms that were involved in our reaction should be checked for formal charge. Those atoms would be what I'm calling our red oxygen, our hydrogen, and our blue oxygen. So we get 3 atoms that we have to check because those 3 atoms were affected by our arrows. Our red oxygen started neutral. Then what did it do with electrons? Shared them with somebody else. Okay? If I've got $5 and share $5 with you, do I still have $5? No. Okay? I've lost some money. So what does that mean? The oxygen was neutral and it's lost electrons. It is therefore positively charged. What happened to the hydrogen?
Lost and gained, so it's
It gained electrons from our red oxygen, but then it also lost electrons from the bond that it used to have, which meant its charge does not change. Since it was not charged to begin with, it's not charged to end with. The blue oxygen started positive, but what happened? Gained electrons, it is therefore neutral. In those approaches, we didn't have to calculate formal charge. What we were using is our understanding of what the curved arrows meant to lead us to that charge. So we don't have to have memorized bonding patterns. We don't have to calculate valence electrons and all that mumbo jumbo. Does that make sense? Okay. So, to the question, which of the following is an acid-base elementary step? We said acid-base was just the transfer of a hydrogen. Is that what happened? Yeah. I had a hydrogen located on our blue oxygen, and that hydrogen is now located on my red oxygen. All that's happened is I've transferred a hydrogen from one place to another. I've not changed any other bonding patterns. That's my acid-base reaction. Or acid-base reaction, and it's an acid-base mechanistic step. Kind of, sort of? Okay. I'll walk through the other 2. Can I delete C? Take a look at purple first. What's happening? Our red arrow is starting at the lone pair on the oxygen, and it's moving it into the space between the oxygen and the carbon, which means I now have another bond. What happened, whoops, with my blue arrow? My blue arrow started at the sigma bond connecting the carbon to the other oxygen, and it's now moved it solely to the oxygen, which means that sigma bond is no longer present. The other atoms didn't change, and I now have that lone pair on that oxygen. All I've done is change the location of those electrons. Make sense? Last thing we do is account for formal charge. Red oxygen lost electrons, positive. The blue oxygen gained electrons, would be negative, except it started positive, so it goes neutral. Okay? The last check that I could do, charge on my product side is positive. Charge on my reactant side is positive. As long as the charges balance out, we've done everything correctly. That won't always work because organic chemists are notoriously horrible at balancing chemical reactions. Okay? Sometimes we do it, sometimes we don't. So you can't 100% rely on it, but it's a decent kind of safety check for some of these. So what happened in this scenario? I formed a pi bond and I broke a sigma bond. The formation of a pi bond is what type of chemical reaction? That's an elimination, which is a little bit weird because if you think elimination, you would think, wouldn't I lose something? We are losing something. We're losing this blue molecule from the parent, but the result of that elimination is that I have formed a pi bond. Okay? So the reaction would be an elimination. What's the mechanism? Well, it's still an elimination, but now I have to know which elimination is it. Okay? In this particular scenario, it is the loss of a species that has electrons. That would be a nucleophile elimination because we've lost a negatively charged species. Negative being in air quotes because it's not formally negative, but it has the electrons. Kind of, sort of?
Yeah.
Is there a question there? Or are you just processing, Jennifer?
I'm processing.
Okay. Should I leave it up there instead of erasing it?
No, I'm good.
Okay. I actually have space, so now I don't feel like I need to erase it, but what happens in B? Okay, again, 2 arrows. If we look at our red arrow, what happened? I'm starting my arrow at the bond, and in particular the pi bond, because the pi bond is higher in energy, and I'm moving that up to the oxygen, which means the oxygen has now gained electrons. If we're now working along as we do this, we could say that that oxygen would be negatively charged. Okay. The blue arrow becomes the tricky one. That blue arrow is saying we're taking the electrons in the sigma bond between hydrogen and aluminum, and we're sharing them with the carbon. Okay? So what that does mean is I'm going to have a new bond here. The question becomes is what atom is it connected to? Is it connected to the hydrogen or is it connected to the aluminum? Okay? If you don't know, this would be one of those cases where, well, we draw it and see what happens. We either draw it with the hydrogen or we draw it with the aluminum. And we would try and decide which one of those options was better. That becomes really advanced because what that's now moving into is the chemistry of our aluminum. And if we look at the Lewis structure for aluminum, does it want 8 electrons? No, aluminum's in that boron category. It's happy with 6. It turns out that the reactivity here, hydrogen will take the electrons away from the aluminum. If hydrogen takes the electrons away, what I get is this scenario where the hydrogen's connected. What does that mean happens to the aluminum? Well, that means the aluminum has now lost those electrons.
That's AL.
That's Al, yeah.
I thought that was an N.
Oh, No,
why I
that's
said
AL.
close.
I could see an N. Yeah, that makes
My
sense.
bad.
I should have adjusted the zoom on it. I apologize for that.
That's the reason I said close.
Right. So now if we go through and look, what happened to the aluminum? Okay. Should it be positive or neutral? You're right. It lost electrons. Shouldn't it be positive? What charge did it start?
Negative.
Negative. So it lost electrons. It's now neutral.
I was doing it with the pen the whole time.
Okay. Kind of, sort of. And now what do we have? We now have our products of that particular reaction. What happened in the course of that reaction?
Hydrogen was transferred.
Ooh, and this becomes interesting. Isn't this a transfer of a hydrogen?
A pi bond.
Acid base is transfer of
H plus.
H plus. And we're saying, oh, why are you saying oh, Ty?
Because it's not H plus.
This wasn't H plus, this was H minus. So yes, this is the transfer of a hydrogen. It's not hydrogen ion per se, the cation, it's the anion hydrogen. This doesn't fit the acid-base definition. If we add to that, why else does it not fit the acid-base definition? What else changed?
Breaking of a pi bond.
We broke a pi bond. So the breaking of that pi bond would suggest this reaction was an addition. Which type of addition was it? What caused the pi bond to break? Was it a negatively charged species or a positively charged species? What charge was the hydrogen? Negative. Which means it was a negatively charged species, which means this was a nucleophile addition. This is why it was so important to know the definition of those terms, because it's negative. That's nucleophile. You can now classify those mechanistic steps faster and more efficiently. Make sense?
Yeah.
Okay. Means we move on. Other questions?
Where in the slides does it show mechanism?
That's the button I wanted to push. When we go to the slides, I just realized all my grunting and groaning is recorded for posterity. That is so obnoxious. Slide 32.
Okay.
So slide 32 lists all of our mechanistic steps. Okay? And you're not going to be particularly excited about it because it's a lot of them. Okay? We get, that's the category. I was like, that's not a name. Heterolysis, electrophile addition, nucleophile addition, AB for
Acid base.
acid base, SN2. We just need to be able to identify it, so don't stress necessarily what those symbols mean. The S, the N, the 2, though the people in lab don't really get a lot of excuses because we said what those were. Right? E2, same deal. We don't stress necessarily about those meanings, just realize that you're responsible for knowing what the pattern is.
What does it mean? It's just,
Substitution nucleophile type 2.
okay.
Well, technically it's substitution nucleophile bimolecular. I'm pretty sure you didn't want to know that. E2 is elimination bimolecular. How many people took 152? The two of you. So you two know what bimolecular means theoretically, if you remembered that from 152. Okay? Everybody else is like, what the hell are you talking about? This is a weird class to teach.
So the 2 means bimolecular?
It means bimolecular. I could say potato. Do you know what bimolecular means?
No. But
If you look it up, that's what it means. Right? I'm not making that part up. Coordination, electrophile elimination, and nucleophile elimination. So you'll note that the reaction names show up in some of these. S, substitution. E, elimination. Addition, eliminations. Right? So if you know those reaction types, you can start to classify some of these a little bit easier. Okay? You also get individual examples. So the subsequent slides go through and look at an individual example for each one. And so this is all in the play posit. You're looking at each of these things and a classic example of what that means.
I was just confused
Okay.
because I didn't have any idea what the SN2 and E2 meant, so I'm like,
Oh, yeah.
like,
And it doesn't matter that you know whether, I want you to know that it means substitution and that it means nucleophile, that it means the two, I don't think you need to know.
okay.
Okay? Yeah, which is a little bit painful for me to say because I want you to know that, but you don't need to know it for the sake of the class. Okay? So the play posit gives you those examples and walks through them. What I'm planning on doing both today and next week is we're going to just pull up reactions. What is this mechanism? What is this? Looking at those pieces and trying to identify those categories. Make sense? Okay. The play posit, and we actually just had a question on this, but the play posit went over this, and it's timed weirdly here. So we're just going to do it this way. Remember that addition that we did earlier? That first one in identify our acid base mechanistic step? This one with the HBr? And we said which result did we get? And we decided that based off of the stability of that positive charge. Stability of the positive charge. That's where it's coming from. Right? So if we understand our ion stabilities, we can predict the different products that come out. That's why this is so powerful. If we understand how to categorize those reactivities. Okay? And so when we look at this, all of these are positively charged things, but how are they different? Well, it's the amount of carbons they have around it. Officially, the bottom one is called a tertiary carbon. Why tertiary?
That is 3 carbons.
3 carbon, tert is tertiary. I think I meant to say something else, but I'm not positive what it was. The second one is secondary because it has 2 carbons. The next one is primary because it has this, you are already guessing them, primary. And then the top one, what do I like to call it? Zeroary, which of course sounds stupid, and that's why nobody calls it zeroary. They call it methyl. Okay? But I would argue zeroary fits the pattern better because it's not connected to any other carbons. And if we're looking at now the stability or the instability, those are all positively charged. Well, positively charged things want electrons. So what would make them more stable? Give them more electrons. So we just look for the difference between each of these. We first said where the charge was. I don't see a difference there. Then we look further out. I don't see any resonance. I don't see any induction, which means we move into the kind of O-carp category, which is me being funny with changing the letter order around, that you can be creative on your own and figure that out. Okay? For that category is a substitution effect. It's a very small effect in the grand scheme of stabilities, but it can manifest in large ways in very particular scenarios. And all we're doing is saying, well, what's the difference? Well, carbon, 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 each of those has 4 electrons. There's 12 electrons around this. There's 9 electrons around this. There's 6 electrons around this. There's 3 electrons around that, which would suggest the carbocation tertiary should be more stable because it has more electrons nearby. That's all you're evaluating. Okay? The play posit, I don't know the play posit actually provided the answer. Oh, son of a... What happens if we now switch to an anion? An anion, those carbons are now all negatively charged. Well, what makes an anion reactive?
That it wants to give away electrons.
It has too many electrons. Okay? So ideally we could move those electrons somewhere in the structure. Well, we can't move them. That's resonance. We aren't talking about anything within resonance. We're looking at a substitution effect. So again, what's the difference between the tertiary and the zeroary?
The top one is the most stable.
Because
Because it has less electrons
there's less electrons in that same space. That makes the top one more stable. So if we understand the differences between positive and negative, what makes one reactive or what makes each of them reactive, we now know how to stabilize that reactivity, and we're just looking for how that effect is manifested within the solution. Okay? So all of the ranking systems that I kind of push at you, this thing, are just saying, where should you start your focus? You start looking for charge. Then you look to see if there's a size effect. Then you see a molecule or an electronegativity effect. Then you can see molecular size, molecular electronegativity. And then if you're really stuck, that's when you move into this last category. This is the substitution pattern that we just explained for tertiary, primary, secondary, now out of order. Okay? Hybridization can show up in here that I don't think we'll talk about that as a potential issue, but we might. Okay? It would be more accident, like, whoops, there it is. Sorry, let's talk about it. Okay? But I don't think I would explicitly ask it on an exam question. Okay? So all of these are just kind of, how do we think about, where should we start thinking about when we look at reactivity? That's it. So all is just a bunch of definitions. Now we just apply definitions again and again and again and again and again. Kind of, sort of? Okay. This slide just scares me. What's the difference between these two reactions?
Where the charge is located on the bonds
Why did the charge change places?
with the hydrogen.
Okay, so what's the difference between these two reactions?
I'll call it the second, the third hydrogen. The third oxygen has the hydrogen on the top, the second oxygen has the hydrogen on the bottom.
Okay, what we're talking about doing, in that top case, we're taking this hydrogen and what are we doing? What happened to it?
We moved to the other.
We moved it to the other oxygen. How did we move it?
We shared the electrons on the right oxygen with that
The
hydrogen.
right oxygen shared electrons with the hydrogen, which now exceeds the octet on that oxygen. So what happens? Or on that hydrogen?
It bonds to the other.
What happens to the bond between the hydrogen and the oxygen?
The oxygen then takes the electrons.
That oxygen has to take the electrons away. So the result is we gain a lone pair on that one, and we would gain the positive charge on the other one. Okay? So what does that mean happened? This molecule acted as what?
The acid.
This acted as an acid. What did the other one act as?
Base.
A base. What happens in the bottom reaction?
The big molecule is the base and the tiny molecule is the acid.
How do we know which one should be acting as the base, which one should be acting as the acid?
Whichever one donates the hydrogen.
Whichever one donates the hydrogen. So you're saying if I mix these two, if I look at it this way, this molecule acts as a base. If I draw it that way, then magically the solution, when I mix those chemicals, it does something different. So I mix these things in a beaker and I put them on the beaker and I say, I'm going to draw it this way. Ta-da, the beaker did what I said. I'm going to draw it the other way now. Oop, the beaker changes its chemistry. Is that how it works? No. Chemistry happens on its own. Our drawing has to match the chemistry. So how do we know which one is more correct?
They both have.
No. Only one of these is valid. This one there's a cheat answer on that you could pull off. Back in Unit 1, I asked you that you should memorize. I asked you to memorize a decent amount of stuff, but there was something I asked you to memorize, particularly when it came to structures. Not the bonding patterns, more advanced than that. What did you suggest, Shay? Same thing. Names of what? Close enough. Our functional groups. You're responsible for naming your functional groups. What is that now red highlighted functional group? A carboxylic what? What do you think it's going to act as? An acid. Okay, so if you knew the name, you knew what its chemistry was. Okay, if you didn't know the name, though, you'd be stuck in the water or stuck without knowing what's going on with it. Okay, on top of which, the name comes into existence because we know the chemistry, not the other way around. Okay, so what about this top reaction makes us go, that reaction makes more sense than the bottom reaction? What we're doing is comparing back and forth between it. This is neutral, 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 neutral. Is there a difference there? No. This is charge, 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 charge. Is there a difference there? Not really, but what do we know about all of our reactions? They want to minimize charge. So given these neutral species, when they react, they're going to produce the products that have the smallest charge. Like, well, they're all the same charge, Mike. That's stupid. All carbocations were positively charged, yet were they all the same stability? No. So now the question becomes, we're comparing positive to positive or negative to negative. Which one do you want to do? Why negative to negative? I completely agree with you. Thank you for saying that and not positive, because I don't have a good answer for not positive. What does negative mean? It has electrons. What is everything we've talked about the entire flippin' semester been about? Electrons. That's why we look at the electrons. So look at the negative thing. I want to compare this negative to that negative. Well, how do I compare? Well, where do we start?
What they're connected to.
Close. Charge. They're both negatively charged. That was a stupid place to start. Okay, what's the next thing after charge? Size. What atom is holding the charge? Oxygen versus oxygen. That was also a stupid place to start, Mike. Oh, you got to work your way through the list. That's how it works. What's the next thing on the list? Electronegativity. Oxygen versus oxygen. Okay, what's the next thing on the list? Resonance. What does resonance mean? Whether you can move the electrons. So let's take a look at the bottom one. Can I move the electrons there?
No.
Why not? I exceed the octet on the hydrogen, so I can't do that. How about in the top one? Could I move the electrons here? I exceed the octet, but you were actually saying, yes, that's okay. Why is that okay?
You just have to do another step of transfer.
Exceeding the octet isn't the problem. It's exceeding the octet and having no way to fix exceeding the octet. That's the problem. Up here, do I have a fix? Yes, I can move those electrons up there. What does that mean?
The other oxygen.
This one has resonance. What does the resonance do to the negative charge?
Moves.
Makes it more stable. Reactions minimize charge. If I mix these neutral species together, which one of these products would I prefer to produce? The less charged one. That's neat. Okay? I just guess. I just throw it together, see what happens. Oh man, that was ugly. Yeah, that's how it works. Almost everything we do is relative. You have to draw multiple things, and ultimately you have to draw wrong things to compare them to the right things. That's challenging. That's why we said at the beginning of the semester, you got to draw more. Dang, sorry, I missed that. We're done. Okay? With this, there's other ways to predict, because I'm not sure I really want to get into all the other stuff, That's dealing with this big K, which is referencing equilibrium, and I forgot my thing doesn't do it. Okay. Oh, lovely. You can look at your big K, which we can call Ka, which references pKa. Big pKa's mean they're weak acids. Small pKa's mean they're strong acids. I think, actually, now that I think about it, there's a question in the active. No. It's in the week 8. It's in the week 8 worksheet that asks about pKa's and what it means for reactivities. Okay? So, oh, there might have been one in active 4 too?
Yeah, just
Dang.
one, but it made sense.
It made sense. Okay, well, that's good. Ultimately, it's looking at the reactivities. Small pKa means strong acid. Big pKa means weak acid. What does that mean? It can be useful to know the pKa's of your functional groups. So when you look at a carboxylic acid of 4 versus the alcohol at 15, carboxylic acid is more acidic. It should act as the acid. The alcohol should act as the base. Right? So if you have pKa's memorized, it can help. It's up to you.